Welcome to section 15.9. In this section, we are going to be looking a little bit at the deeper reasoning behind these different coordinate systems that we use and how we can convert between systems when we're doing double and triple integrals. We're going to be looking at a little more theoretical concept and seeing directly how it relates to the work that we've been doing. So to start us off, in Calc 1, so we're going to think back, we use a change of variable, which we're going to refer to as a substitution, to simplify an integral. So this would be like what we call a u sub, right? A u substitution is what we're used to. If we reverse the roles of x and u as we think of them, so instead of like u equals some function of x, we basically have, instead of f of x, we have a function of u taking the place of the x. This integral would become f of g of u times g prime of u du, right? So this is the basic form of like the u substitution. This is how the chain rule looks, right? You get times the derivative of that inside function. This is where x is equal to g of u, a is g of c, and b is g of d. So we can convert between two different variables, right? We can solve it all in terms of x, or we could solve it all in terms of u, and they are related via this substitution, so we can make sure that they are equal, right? Make sure that they are the same thing, right? They don't look exactly the same, but they will get us the same result. This can be rewritten in terms of basically just x's. We're kind of getting rid of the g notation. So f of x of u times dx du, so derivative of x with respect to u. Okay. We'll see how that is relevant in a little bit. One example of change of variables in double integrals that we have already seen is polar coordinates. Okay, so we're going to be talking quite a bit about polar coordinates today because it's just something that we are already familiar with. So polar coordinates is a change of variables because we're turning x's and y's into r's and thetas, okay, or vice versa. So when we set up our double integral over r of f of x, y, dA, that's equal to the double integral over s of that same thing converted into polar, right? With r cosine theta, r sine theta, r dr d theta. So this is where s is a region in the r theta plane that corresponds to the region r in the xy plane. In general, we consider a change of variables given by a transformation t from the uv plane to the xy plane. So this is t of uv equals xy, where x is a function of u and v and y is a function of u and v. So the transformation is basically the mechanism that we use to move between the different types of variables. So if we have variables u and v, we want to convert them into x's and y's. We use the transformation t. Okay, it'll define some rule or some relationship between them. Okay, and this is where x and y are both written in terms of u and v. We usually assume, at least at this level, that c is what we call a C1 transformation. Meaning that g and h, so this would be like g and that would be like h, have continuous first order partial derivatives. Okay, so we don't have to worry about taking partials. We know that they will still be continuous. If we perform this transformation, so t of u1 v1 equals x1 y1, x1 y1 is what we call the image of u1 v1. So if you think about this in terms of, think like an actual image. Like if I take a picture of something, right? So I've got all these people standing here, excited to take a picture. You take a photo of them. So if I'm holding the photo, you can see here, this photo is a good representation of these two people right here, right? When I look at this photo, I understand that I'm looking at this group of people. However, I think we can all agree that this photo is not actually this group of people, right? They are not the exact same thing, right? This is a piece of paper with like ink on it, right? Little like particles that are all in the proper arrangement and color in order to produce an image of what we are seeing here, right? So it's the same kind of idea with transformations. So these two things, right? Think of them as like R and S, two different regions, two different sets of variables. They are not exactly the same thing, but they both represent the same thing. Okay, so whether it's the actual people or it's the image or the photo of the people, it's not exactly the same thing, but they represent the same thing. And that's the idea with the transformation, is we can move back and forth between the two different spaces, understanding that they both represent the same thing. Now, an interesting thing about the transformation, if no 2 points have the same image, then t is said to be 1-to-1. So just like a function. If t is 1-to-1, then it has an inverse transformation, which is abbreviated t to the negative 1, from the xy plane to the uv plane. So we know that we have a transformation that turns uv values into xy values if there are no 2 points that have the same image. So there's no repeats. Okay, then this x1, y1 will go back specifically to this u1, v1. So if that's the case, we can go from the xy plane to the uv plane, and we may be able to solve for u and v in terms of x and y. So if we have a 1-to-1 transformation, we can go back and forth between the two. So note, t transforms S into a region R in the xy plane called the image of S. So let me pull up my visual here. So we have the region S in the UV plane. Okay, here's a point U1, V1. We use T, the transformation, to go to R. This is a region in the XY plane. Here's our point X1, Y1. We could then go back using T inverse if we know that it is 1-to-1. And from here, we could take every single point in S, transfer all of those points over to R, and we would have our transformation. These two regions, even though they don't look exactly the same, they represent the same thing, and all of the points of this one would get transformed into all of the points of this one. Okay, so that's the relationship that we're establishing. Now, the nice thing about the way that these transformations are set up, if we know that everything in S is going to transform into everything in R, what we can do is we can actually look at the boundary of S, transform that into the boundary of R, and all of the points that were in S will be the same points that are in R. So we don't actually have to go point by point. when we're transforming. We just have to transform the boundary, transform the outside edges of the region, and all of the points within those boundaries will stay within the boundaries as we transform them. Okay, so again, we don't have to go point by point, just transform the boundary, and the points inside will stay inside. So let's take a look at an example of this. So, and I've already got a lot of kind of pre-written stuff that we're going to go through here because this is kind of a lengthy one. So a transformation is defined by the equations x equals u squared minus v squared and y equals 2uv. Find the image of the square S where u is between 0 and 1 and v is between 0 and 1. So you can see right here, I've got the square S. So S. So note the transformation maps the boundary of S into the boundary of the image. So we're going to find the images of the sides. So you can see I've already got them labeled S1, S2, S3, S4. So we're going to just transform these 4 sides. And we know that whatever region we get out of that, all of the points inside of S in this shaded region will still be inside of R, the new transformed region. So we're going to go one line segment at a time. We're going to start with S1. So you can see right here, S1, this is where V equals 0. Okay, V is the vertical axis, so V is 0. U is going from 0 to 1. So, using these equations, back up here, x is u squared, because v is 0, y is 0, and x is going from 0 to 1, because u is going from 0 to 1. So S1 maps a line segment from 0, 0 to 1, 0. So that's nice. This one is the line segment from 0, 0 to 1, 0. It maps back the same exact thing again, right? Because then as you start plugging in numbers from 0 to 1, you end up getting from 0 to 1 for u, you get values of 0 to 1 for x. Even though this is a u squared, it's not forming a parabola because in order to make a parabola shape, the y has to be going with the parabola squared. But y is not. Y is just staying completely flat. So it's still a flat line, x going from 0 to 1. Next up, we have S2. So this one's a little trickier. So we've got a vertical line segment, so u equals 1. V goes from 0 to 1. So if we substitute in u equals 1, we end up getting x is 1 minus v squared. Y is 2v. Now if we rewrite this a little bit, so we know that v is 1/2 y. Substitute that back into here to get this equation. So we get x equals 1 minus 1/4 of y squared, which as you can see, this is a sideways opening parabola, right? Because x is single power, y is the square, with x going from 0 to 1. So S2 maps a parabolic arc from 1, 0 to 0, 2, right? So when x is 0, then we start at the point, when x is 0, that's actually at this point. So technically x is going from 1 to 0, but it all will work out the same way. So we go from 1, 0 to 0, 2. So right when x is 1, y gives us the 0, and then we get 0, 2 as well. All right. Next up, S3. S3 is very similar to S2, so it's the same kind of argument, except now v is 1 because we're up here on S3. So v is 1. U goes from technically 0 to 1, but same kind of idea here. You can see that it's actually going from 1 to 0, but we want to put it in numerical order. So we have, similarly, we get this equation for another sideways opening parabola with x going from -1 to 0. So S3 maps to another parabolic arc from 0, 2 to -1, 0. And then S4. S4 is very similar to S1. So it's a vertical line segment where U is 0, V goes from 0 to 1. So we get these equations, which still map to a line segment. So all four of these, I've got the diagram right over here, map to this shape. So we've got R1 maps to that line segment, R2 onto this parabolic curve, R3 onto this parabolic curve, R4 onto this line segment. So we've got that square shape up above transformed into this kind of half teardrop shape down below. So this is R. Okay, so we can say that R is the image of S. So when converted from U's and V's up here into X's and Y's down here, this is what the region looks like. So every point in this region corresponds to a point in this region. So if you plugged in any U and V that you want into those equations, that point from here would transform to some point down in here. Okay? And we know that that will work because we already transformed the entire boundary. Okay? So every boundary point up here on the square has a corresponding boundary point down here on this curved surface. Okay? Or this curved region, excuse me. Right? So we can transform different coordinate systems, different sets of variables into x's and y's, and vice versa. Now, to see how this impacts our integration, we need to introduce a new piece of terminology, a new formula. And this is the idea of the Jacobian of a transformation, given by this formula. The Jacobian of the transformation T, given by x and y in terms of u and v. The formula, it looks like partial differentiation right here. This is just kind of a general notation, but it looks like partial of xy over partial of uv. This is equal to this 2 by 2 determinant. So remember determinants from when we did like cross products a long time ago. 2 by 2 determinant with the corresponding partial derivatives in its components. So partial x respect to u, partial x respect to v, y with u and y with v. Then we take AD minus BC, so partial x respect to u times partial y respect to v minus x with v times y with u. This formula, this process, arises in the calculation to approximate the area of a region R that is the image of a region S that has been transformed. So when we are transforming the region S into R, like we just did, if we were going to start doing calculations with it and integration with it, we would have to include the Jacobian in that calculation. Because again, S and R, as you can see back in this example, S and R are not exactly the same thing, right? They don't look exactly the same, but they represent the same thing. So when you're doing the transformation, you're not going to have a case where every single point in S is equal to exactly all the points in R, right? They correspond to each other, but they're not equal to each other, right? Like this one over here has, a 0.11 in it. This one, 1,1, is over here, outside of the region. So it transforms, but it's not exactly equal. In order to get the transformation done right, this is where the Jacobian comes in. So when we're moving things between different coordinate systems, between different regions, we need the Jacobian in order to convert properly between them. So let's take a look at how this is going to work in our integration. So suppose T is a C1 transformation whose Jacobian is non-zero that maps a region S in the UV plane onto a region R in the XY plane. Suppose F is continuous on R, and R and S are type 1 or type 2 plane regions. In other words, they are integrable. Suppose that T is 1-to-1, except perhaps around the boundary of S. Then the double integral over R of f of x, y, dA equals the double integral over S of f in terms of u and v times the Jacobian with respect to u and v. So we can convert between x's and y's and u's and v's. If we go back and look at the very beginning of this section, we talked about the original Calc 1 formula of the u substitution right here. This had f of x of u times dx du, right, when we converted between x's and u's. If we look at this one now, this is basically the same thing here, right? Except we've got two variables, and instead of dx du, because we have multiple variables, so instead of dx du, we have the absolute value of the Jacobian. So that's absolute value xy respect to uv. So if we look at how this is used in practice and how we've actually been using this without even really knowing that we're using it, consider polar coordinates. A transformation T from the r theta plane to the xy plane goes like this. So x is r cosine theta, y is r sine theta. T maps an ordinary rectangle in the r theta plane onto a polar rectangle in the xy plane. So if I pull up these graphs here, so you can see in the r theta plane, r goes from a to b, theta goes from alpha to beta. These are all constants, so we're going within the confines of a rectangle, right? This is a rectangle. When we transform the values into our polar rectangle, we get r goes from a to b, right? That's the radius of the circle here and the circle here. Theta goes from alpha to beta. Those are the two angles. This is why, way back when we first learned about the concept of a polar rectangle, we said that it has the properties of a rectangle, the bounds are constant just like a rectangle, but we kind of just waved it off and said, yeah, it's kind of a rectangle. Well, the reason it's called a polar rectangle is because in these polar coordinates, r and theta, it actually is a rectangle. It is a real, honest-to-goodness rectangle in r and theta that when we convert it into x's and y's, looks curved. But in terms of r's and thetas, it is an actual, real rectangle. Now, if we look at the Jacobian of this transformation, see if I can keep those functions up there. This is partial xy respect to r and theta. We take the 2 by 2 determinant. So it's partial x with respect to r. So that's going to be cosine theta. Partial x respect to theta. So that's negative r sine theta. Partial y respect to r is just sine theta. Partial y respect to theta is r cosine theta. So we take the determinant, we get r cosine squared theta minus negative, so plus r sine squared of theta. So that's r times cosine squared plus sine squared of theta, which a trig identity tells us that that's just 1. So this is just r, which we know will be greater than 0. So when it comes to setting up the double integral in polar coordinates, everything gets converted to r and theta times the absolute value of the Jacobian. Absolute value of this Jacobian is just r, so we get r dr d theta. So the r in that polar coordinate double integral, when we make the conversion between the two, what we were actually doing was finding the value of the Jacobian, okay, without knowing that we were doing that, because there's a lot of information you need to get to this point. But that's what it is. So this r value, the reason it's there is because when you're making the conversion from x's and y's into r's and thetas, or vice versa, there's a price to be paid. The Jacobian is that price. You can't just directly switch x's and y's into r's and thetas because they're not exactly the same thing. When you make the conversion, the Jacobian is the price that you pay that allows you to switch them, that allows you to turn x's and y's into r's and thetas. This also works in 3D and for triple integrals. So if we have t, a transformation, transforming s, which is in UVW space, onto r, which is in XYZ space. So we have x, y, and z are all functions of u, v, and w. The Jacobian is a 3x3 determinant, where we take the partials of x with respect to u, v, w, the y's, and the z's in this 3x3. So this is just like how we used to compute a cross product, right, with like I, j, and k in that first row. Same process. And our triple integral formula, the conversion that we make, everything gets converted into u's, v's, and w's times the absolute value of the Jacobian. We have seen one other type of coordinate system where we have used this information, and that was spherical coordinates, just in the last section. So we know x is rho sine phi cosine theta, y is rho sine phi sine theta, z is rho cosine phi. If we set up the Jacobian using these three, so we take the partials of x with respect to rho, phi, and theta, y with respect to rho, phi, and theta, and z with respect to rho, phi, and theta, we get this 3x3 determinant. So these are all the partial derivatives with x, with y, and with z. And I'll spare you the boring details of me doing the determinant, the 3x3. If you want to practice with it, you want to try it out, that's great. Just take first component times the 2x2 determinant, and then go the second, go the third, etc., just like a cross product. But we end up getting out negative rho squared sine phi from that calculation. And of course, when we do our triple integration, we're taking the absolute value of the Jacobian, so the negative goes away, and we're left with rho squared sine phi, which is exactly what we were including when we converted into spherical coordinates from xyz's into rhos, thetas, and phis. So this is exactly where that comes from. This is where we get our rho squared sine phi. And that brings us to the end of chapter 15. So this has been a lot of setup up to this point of functions of multiple variables, doing partial derivatives, now doing multiple integrals, now looking at transformations and seeing kind of the background of these different coordinate systems and how we integrate with them. When we come back in the next and final chapter, we're going to start putting all of these ideas together in order to do some vector calculus. So it's going to be a lot of good stuff coming up. I look forward to talking with you all then.